All right. So what I thought I'd do is kind of whip through a presentation on SpaceX. Some of you are probably aware of the details of what we're doing, and some are probably less familiar. So I'll go through it fairly quickly and then try to leave as much time as possible for any questions. And you're welcome to ask me, anything about the rocket or the business. And I think I can probably answer just about everything. Maybe a few confidential items. So, basically, SpaceX. I started SpaceX because it seemed to me that we weren't making the kind of progress we really needed to make in the cost of access to space. And if we don't make cost, I mean, I'm sort of preaching to the converted here. Normally, the room is not quite as converted as this room is. But so I'm telling you things you already know. But so long as it costs us hundreds of millions of dollars to put a few people in space, or not even faraway space, just 300 or 400 miles above the surface of the Earth, we're never going to get anywhere. We're not going to become a spacefaring civilization. And I think probably, I mean, what I really think is the overriding goal, and what I suspect most people in the room think is certainly is an extremely important goal, is becoming a spacefaring civilization, ultimately becoming a multiplanetary species. And if we're not on that path, then we really need to get on that path. So, given that the fundamental obstacle to that is really the cost of getting there, they weren't making progress in that direction. That's really why I started SpaceX. But before actually formally starting the company, I put together a group of engineers that have been involved with most of the major rocket developments in the U.S. and had some familiarity with the way the Russians did it. And in fact, the current NASA administrator, Mike Griffin, was on that feasibility study group. So I'm very glad to see he's the new administrator. We sort of sat around over a series of Saturdays in early 2002 and tried to figure out, is there anything fundamental? Because I didn't really know anything about rockets at that time. Is there some sort of really difficult physical thing that makes it fundamentally as expensive as it is, and you can't make improvements? And it quickly became obvious that there really isn't anything fundamental that prevents chemical rockets from being much cheaper than they are right now. To give you an example, the propellant cost of the Falcon 1, what it costs to fill the gas tank essentially, is about $30,000, and that's on a $6.5 million launch initially. We want to keep driving that launch cost down, but in airlines that is a dominating factor, often the predominant factor in cost. Whereas for rockets, it's an accounting error. And we need to get to the point where where it's not an accounting error, and actually, unless you have really bad accounting, and it's actually where propellant cost actually matters. So anyway, so the way I usually describe it to people is that the goal is to be kind of like the Southwest Airlines of the space business. And when Southwest Airlines came in, airfares were really expensive. And Southwest came in often airfares that were often, 15-20% of what say United or Delta was charging. And people at the time said, well, this is really impossible. There must be compromising reliability, or there must be something missing with this picture, or they won't be able to sustain those prices. They're out of business. And the fact of the matter is, Southwest Airlines today is the most profitable airline in the industry. Has a market cap greater than the sum of all of its competitors, and it still offers those prices. And reliability is good, on-time performance is good. So they went in, they really rethought the whole space business, the whole airline business, and so that's sort of a good kind of model to think of what we're trying to do, is rethink the business of space transportation. Now I think we've got actually a greater ability to improve in our case, because we're actually driving the fundamentals of the technology, whereas Southwest Airlines could only improve on the service and had to work with an existing technology base of this, the 737. Anyway, that's the basic idea. And I believe in setting objective benchmarks. So, because if you can't measure it, it's very difficult to figure out if you're improving. And so the benchmark objective is a factor of 10, and to put an actual number on that, it's less than $500 a pound to orbit is the goal. I think we can actually get there before the end of this decade. It's structured like a Silicon Valley technology company because that's how I know how to structure companies. Work well the first 2 times, so hopefully third time as well. A few common things. There's a very flat hierarchy. It's we're just all in fairly densely packed cubes. We have a fairly small engineering team, but they're really, really top engineers in their field. And we have what I call a high signal to noise ratio, where signal is engineering and management is noise. And I think there's a lot of big aerospace companies have a very bad signal to noise ratio. So, and then the big driver in terms of both reliability and cost improvements is simplicity. So that's really our mantra at SpaceX. If we can figure out a simpler, easier way to do something, we'll do it. We don't care about whether it's new technology, old technology, it doesn't matter. We just want to get the job done. Our headquarters are in El Segundo, which is about a mile south of LAX, and we have about 75,000 square feet of engineering and manufacturing space. We actually manufacture the rocket right there in LA, which sounds kind of weird to build a rocket in LA, but we do. And then we do our propulsion and structural testing in Texas. We have a 300-acre propulsion test facility out there, and I'll show you some pictures of that later in the presentation. Some of the slides, by the way, I'm going to go through pretty quickly. Next slide, please. So we made pretty good progress. Our 3rd birthday will be next month in June. And in approximately 3 years, we've designed the entire rocket from scratch, gone through, designed, built, and tested the entire rocket. Both stages, the fairing, 2 new engines, including a pump bed engine. And our engine is actually going to be only the 2nd American orbital booster engine developed in the past 25 years. The other one being Boeing's Delta IV engine, and before that, the Space Shuttle main engine. And we've managed to get a few launch contracts, 2 with the DoD, and 1 with the Malaysian Space Agency, and 1 with a U.S. commercial entity, which is Bigelow Aerospace. And the last one being the Falcon 5 launch with Bigelow Aerospace being a subscale launch of his space station. So that should be doubly cool. And then we also, you may have seen the announcement that we were awarded a $100 million Air Force IDIQ contract, which hopefully will be used to the fullest extent. And I would expect sort of 1 to 2 launches a year starting next year on that contract. I don't know if you saw the last, if you head back 1 slide. Essentially, that prior slide was our facility when we moved in. This is it 1 year later. We're assembling a prototype on the floor. And next slide. And then 1 year after that, the qual vehicle is on the launch pad. And the flight vehicle is actually currently on the launch pad. And we expect to do a hot fire on the pad tomorrow. So, because Delta 4 finally launched, or Delta 2 finally launched this morning at 5 a.m. or whenever it was. And so we're cleared to do the pad hot fire. And then the actual launch should take place as soon as the Titan 4 departs Vandenberg, which is in approximately the August timeframe, or July-August timeframe. Let's see if this works. Just a launch simulation video. I'll skip over the sort of reliability stuff. We think it's very important, but it's very important, but not really trying to sell anyone here a launch, I think. But basically, yeah, simplicity is the key to both. There's, on the cost side, there are several key technical innovations in propulsion system structures, avionics, guidance control, launch processes, and we're a fairly vertically integrated business. We actually literally machine the metal, bend the metal, weld, all that sort of stuff in-house, because what I've discovered is that the aerospace supply chain is so bad that as soon as you subcontract any significant portion of that work to somebody, it becomes very expensive. So we've generally found it's more efficient to be vertically integrated than outsourced. And so Falcon 1 capability is just over 1,000, like 1,500 pounds to low Earth orbit. The Falcon 5 capability is about 6 tons. Actually, we'll get to that later. The optimization in the case of Falcon 1 was really in terms of a cost per flight to orbit. So it wasn't a cost per unit mass optimization. It was what is the smallest useful vehicle that we can build and deliver satellites on, and we concluded that was yet to be at least sort of 1,000 pounds to LEO, and we ended up exceeding that, going to about 1,500 pounds. Total cost per launch is about $6.5 million all in. Both stages LOX kerosene. One noteworthy element, actually next slide, is that the first stage is intended to be reusable. It comes back by a parachute to a water landing. The pricing does not include any assumptions for reusability. I'm actually fairly confident that reusability will work, provided the parachute opens. I mean, I think if the parachute opens, and I don't think the seawater is going to hurt the rocket. You see what it goes through on the test stand and on the launch pad, where it gets deluged with water, high pressure water, and in our test stand in Texas, I mean, we've had sleet, snow, rain that's hitting you sideways at 35 miles an hour, extremely high winds. So I think if it's provided we get it back, I think it'll actually be require very little refurbishment in order to launch a game. The first stage engine, which we call Merlin, is those are the approximate specifications of it. A lot of this is on the website, but basically it's a roughly 75,000 pound thrust sea level engine, and of modest performance. I mean, one of the things that we haven't tried to do is try to achieve the highest possible performance. Our goal has been to create something which is a reliable truck, essentially, rather than a Ferrari. So we haven't produced, for instance, a stage combustion, super high ISP engine. This is, you need to be pretty good, but to get to orbit at all. But you don't really have to push the envelope any further than we pushed it here. Next slide. Our upper stage engine also LOX kerosene, and similar in architecture to the first stage engine, except that it doesn't have a turbo pump, and it's a low pressure engine. So Falcon 5, which is the Falcon 1 development has really been winding down now for the past several months, and essentially is almost complete at this point. So the development focus for about the past year has been more on the Falcon 5, which is our medium lift vehicle. The Falcon 5 is approximately in the class of a Delta II Heavy. It's also intended to, at least from our standpoint, be safe enough to carry people. It has engine out capability, so you can lose any one of the main engines and still make it to orbit. I think that's actually a very important principle, given that airline transportation, almost all airliners have multiple engines. So if you lose an engine, you don't go down. Jet turbines are far more reliable than rocket engines. So if that principle makes sense for jet turbines, it really makes sense for rocket engines. And we expect to be able to accommodate up to a 5-meter fairing as well. So it'll have, really put some pretty big stuff up there. And these are some pictures of our test site. That's our propulsion test site at night. Next one. That's our main structural test stand for Falcon 1. So we actually have a large steel brace which surrounds the vehicle, and the vehicle is hydraulically bent and crushed at various points to simulate flight loads. That's our horizontal test stand. That's a picture of the Merlin engine at full thrust. That's our small vertical test stand where we test the upper stage engine. And that black pipe there is a diffuser, which helps simulate vacuum conditions. It's vertical test stand 2, which is another picture of Merlin in the vertical configuration. And that's our really big test stand. And that's capable of testing basically thrust levels up to about 3 million pounds. So that test stand runs about 100 feet into the air, 70 feet underground. And we hope to use that to its fullest capacity and maybe beyond. So that'll be exciting. And the R in that stands for rocket. So well, it depends on which trajectory. I mean, the 0C3 number, as I recall, is about 1,200 kilograms, something like that. Yeah, it's like about a ton, a little over a ton. I mean, basically, it's about as capable as the Delta II Heavy is that sent the Mars exploration rovers there. So anything that Delta II could throw to Mars, Falcon 5 could throw to Mars. Couldn't really send people if they were alive. It's something much bigger than that. But you could certainly do robotic missions. We don't like to disclose too much ahead of time because, well, frankly, we'd like to, it's more a question of sounding credible than anything else because we'd like to get some things accomplished before we claim we're going to do other things. But the plan is to do a vehicle which is in the class of Delta IV after Falcon 5. And you could apply sort of a common booster core approach to that, and encompass the entire range of the ELV capabilities, so up to about 60,000 pounds to orbit, maybe a little beyond that. I can say that we'll be announcing something fairly significant later this year, as far as much more lift capability than is currently represented. But we'd like to, ideally, I'd like to have Falcon 1 launch before we make any big announcement in that direction. But you can expect that from a strategy standpoint, we're, call it the 7-11 strategy. We're going small, medium, large, and extra large, or big gulp, or whatever it is, super big gulp. So Falcon 1's obviously small, Falcon 5's medium. We'll have the large and extra large. I think range-related stuff is probably, all regulatory stuff combined, I'd say at most 25% of the cost. It's associated with both development and launch. The ablative portion is actually really cheap. It costs less than one of our main valves on the engine. So I don't want to give away sort of really detailed proprietary numbers, but I can say it's really de minimis. It costs us more to hire the tugboat to go out there than it does to replace the ablative. Sure. And by the way, we put out I write a little update every 3 or 4 months. I've been waiting to get the hot fire done before doing the next update. The hot fire that we're planning to do, which hopefully will take place tomorrow, it was originally supposed to take place on May 3rd, and then we had an igniter sensor failure, which we lost that day, and then we have to go behind the Delta II, and so it goes on. Anyway, but it's supposed to happen tomorrow around around 1 o'clock Pacific time. And it's going to be a complete launch simulation, including about 5 seconds of flame on the ground. 5 seconds feels like a long time if you're there, by the way. Then, as far as the actual launch date, we think we'll be ready to go as soon as the Titan IV departs, which is currently scheduled to be around mid-July. So there's a contingency there both on the Titan IV rocket as well as the payload, which is a classified payload. And so we only have limited visibility into that because they won't give you specifics when there's classified stuff involved. But we expect, assuming that they launch in mid-July, we expect the range would give us a launch, because the range has to assign a launch day to us. We assume the range would assign a launch day that is within 2 or 3 weeks of the Titan IV departure. So therefore, if Titan IV left, I'd say basically August would be a good bet. And then as far as Kwajalein, that's actually going very well. We have our own little island there called Amalek. It's the concrete is all, I think the last bit of concrete is getting poured next week. So all the concrete for the pads and the propeller storage and the vehicle hangar and all that sort of stuff is almost all done. We expect to have that launch site active and ready to do something with in the late August timeframe. So if Titan IV gets significantly delayed, then we'll go out of Kwajalein. And we expect to actually have 2 rockets, one at Vandenberg, one at Kwajalein, possibly on the pad at the same time. Anyone outside the space business that's for a rocket, because they assume rockets are made of magic. So if you tell them it's for a rocket, they go like, well, I don't think I'm quite good enough to do something for a rocket. They're like, no, it'll be fine. So we generally, there are some suppliers or aerospace suppliers that do a good job. I'd say like Murata Valves does a good job, for example. Spincraft does a good job of spinning domes. There's a few. So I don't want to sort of paint all aerospace suppliers with the same sort of negative brush. I think there are definitely some good ones out there. But generally, we find as a principle that regular industrial suppliers, if you want something cheap, fast, and it's probably going to work, then you should use a regular commercial supplier. If you want something that's expensive, takes a long time, might work, use an aerospace supplier. It's possible, when we get to the really big propulsion stuff, that we'd want to use some of the NASA test facilities. As a general rule, we don't want to be the ones begging to use facilities. So if we're going to use a NASA facility, then that NASA facility has to behave like we're the customer. If they don't behave like we're the customer, we're not going to work there. If we have to sort of justify why we want to work there, we're definitely not going to work there. I think just for pace of execution reasons, because there's also a lot of paperwork involved with using NASA facilities, we've chosen to use our own facilities. But I think, like I said, for big stuff or where that's it's like one of a kind sort of test facilities, that's probably where it makes sense to work with NASA as far as using test facilities. Sure. Well, it's actually on the website. It's basically it's about 15.8 million plus about $1 million in range-related fees, so you can say 17 all in. And that's for a Delta II heavy class vehicle.
About 12,000 pounds.
A little more than that, yeah, about 13,000 pounds. So it's a little more capability than Delta II heavy. No, we've designed Falcon 5 to be. It's actually consistent with NASA manned standards for as far as safety margins and all that are concerned. It actually exceeds them in most cases. And I think the fact that it's engine out redundancy is is good as well. The G loading is certainly fine. It's maxes out at 5 Gs approximately. I don't think there's any issue with putting people on it.